Afternoon lecture, I have to finish at 4 o'clock, so I start on time. But still a little story at the beginning. So, do you have bears in Korea? Are there any bears in Korea? Bear? Hmm? The animal, the teddy bear. Only in the zoo, yeah. Yeah, so Canada is a bear country, right? And we have two types of bears, which is the black bear and the grizzly bear. And the grizzly bear is really dangerous, and the black bears are much smaller, so they're not that dangerous. And if you go hiking in the forest or in the mountains, then there are certain ways how you can protect yourself for bear attacks. One is little belts, like they're called bear belts, and you attach them to your jacket or to your backpack. And then while you're hiking, you constantly make bimmel, 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 bimmel. So you're constantly making noise to keep the bears away. The other thing is pepper spray. Right, you can have a big spray which is very sharp, and you spray it to the bear if they come too close. Yeah, and then it's also important to recognize signs of bear activity so that you know if a bear was on your path, and so you can look at the droppings of the bears. Okay, so the feces, so the droppings, and so black bear feces, if you see them, they contain lots of berries and maybe some squirrels or some mice fur or something. And grizzly bear droppings, you recognize they contain little bells and they smell like pepper. Okay, so let me continue with this parabolic limit stuff. So I will just summarize the main spectral result now. There are a few more details which I haven't proven, and I will not prove them now. The proofs are all contained in my notes, so if you want to look it up, you can find it there. But then we will be able to move on to the next step. So let me just summarize what we have. So theorem 6. So that's the main spectral result. And then this is in a paper with myself and Hans Othmar in 2000. So we assume the assumptions from before. So assume T1 to T4. So then, and now I have a list of 5 items of properties. So first, so 0 is a leading eigenvalue. Of this operator L, and also L star with unique eigenfunction phi 0 is equal to 1. Then second, all other eigenvalues are smaller. They satisfy that minus 2 mu is less or equal the real part of lambda, which is less or equal minus mu2, which is less than 0. So this mu2, this was this one term I defined in the previous lecture, and it will show up in item, what is it? In item 3. So in the next line I will remind what mu2 is. Important is that this is really bounded away from 0, so they're not getting close to 0. Okay, and then we have 3. So I split L2 into 1 and the orthogonal complement of the constant functions, and for all psi in the orthogonal complement, I have an estimate for L, so then the integral v psi L psi dv is bounded by minus mu2 psi 2 norm squared, and so here's a mu2 again, and now I define what it was. So mu2 is mu 1 minus t norm on 1 orthogonal. Okay, and then 4, what is 4? So then mu2 is also a lower bound for L as a linear operator. So now I have too many L's, but anyways, from L to V to L to V. So now I'm talking about the operator norm of L on as an operator between L2 spaces, and this is bounded between mu2 and 2 mu. And then the last point, so I can start here, 5. Now if I take this turning operator and I restrict it to the orthogonal complement of 1, so then I take out the eigenfunction with the eigenvalue 0. So now this function becomes invertible. Because I took out the 0, this becomes invertible. And this is called the pseudo-inverse. So this has a linear inverse, which I call curly f. Okay, and then it satisfies an estimate as well. So with 1 divided by 2 mu less or equal norm of f on this orthogonal subspace, which is bounded by 1 over 2 mu, 1 over mu 2. So, yeah, so most of this we have proven in the general theory. I did not talk about the inverse yet, and this is a proof I will not show here. So as I say, it's in my notes, and you can look it up. But what we do later is we compute this inverse. So this is something we have to do. All right. So any questions about this before I continue? Okay, so then let's come to the scaling now. So there would be 4. Diffusion limit. And 4.1, let's look at some typical scaling. So I will make some scaling assumptions, basically introduce an epsilon and then make epsilon small. But I would like to relate it to the biology. So what does it mean? And again, I look for E. coli bacteria. This is one of the first examples where this has been done for. And so E. coli bacteria are bacteria which have flagella on the outside. And they can rotate the flagella clockwise or counterclockwise. And if they rotate them counterclockwise, then the flagella align and propel the bacterium forward. So then it looks like this. And it goes like this. If they rotate clockwise, then these flagella spread out and allow the bacterium to change the direction, to reorient. And then it moves again in a certain way. So then an orbit we get is this picture which I've plotted many times now, where we have phases of straight movement, reorientation, straight movement, reorientation, straight movement. And now I would like to kind of collect the scales of what's happening. And we can identify 3 time scales. So the first one is a scale of turns, and it turns out they turn about once per second. So from here to here, the 1 second, 2 seconds, 3 seconds. So once per second they seem to change the direction. So turning. And so the turning time scale is 1 over mu. Right, mu is the turning rate, so 1 over is the average time between turns. And this is in the order of once per second. No, this is second, right? Turning rate is so this is in the order of seconds. And I call this the runtime, and for now I call this order 1. So now I'm on the smallest time scale of the individual movement. So this is a tau run, should be this. Then we can observe a drift time scale of 50 to 100 turns. So if you observe this for 50 to 100 turns, then you see a net drift. I don't have the videos here, maybe I can show some on Friday or so. But after 50 to 100 turns, you see that there's some net spread of these bacteria. So let's call this the drift time. Drift And then this is of the order 1 over, no, this is of the order 100. Yeah, 100. So it's 100 turns, and then if I go to 1,000 or 10,000 turns, then I'm on a diffusion kind of scale. Diffusion is about 2,500 to 10,000 turns. So we have tau diffusion, which is of the order of 10,000. Okay. So if you observe this for 10,000 turns, it really looks like a diffusion process and no longer like a random walk. Okay. So based on this, I do some non-dimensionalization. Yes.
What's the drift?
Excuse me?
Drift. What is the meaning of drift?
A drift, I mean just net movement. So net movement away from where they are, so you can see they.
How far they can
So how far they can get. Yeah. So they covered some distance.
So then why do you use why do you use the unit turns? 50 to 100 turns?
Yeah. So one turn is about 1 second. So 50 to 100 turns is 50 to 100 seconds. Yeah.
So that 1 second, that is somehow physical time length.
Yeah, physical time length.
That's real physical.
It's a real second. Yeah.
Okay.
Right. Right.
So every second they are tumbling.
Yes.
And then if we observe about 100 seconds, we can see there is some net movement.
Yeah, exactly. That's exactly right. Yeah. Yeah. And if we observe even longer, like 10,000 seconds, and it looks like really irregular diffusion kind of movement. Yeah. So it will be more clear if I do this like this here, if I do the non-dimensionalization. So I rescale the velocity with a characteristic speed s. So s is a characteristic speed. And this is about 10 to 20 mu meters per second. So that's the typical speed they move. And then I scale the space by an L, which is a characteristic length scale. And these E. coli bacteria, they show swarming and aggregations. And so I use the scale of these aggregates as my scale L. So L would be a characteristic length scale of bacterial colonies. And this is in the order of 1 millimeter to 1 centimeter. Okay, and then the time scale I relate to a sigma, where sigma is the time scale of observation, which is several hours. So sigma macroscopic time scale of observation. So this is 1 to 10 hours. Okay. So now if I take the transport equation, I'm not going to write it down again, but if I do these rescalings of space, time and velocity, then I get these L's and sigmas and so on into the equation, just from internal derivatives. So I just show you what we get. We get 1 over sigma p t tilde plus s divided by L, and then v tilde times gradient with respect to x tilde p. So this is where all the scaling happened. I rescale t to t tilde, and I get this 1 over sigma. I rescale x tilde, so I get this 1 over L, and I rescale v, I get s times v tilde. Okay? And so then the right hand side is unchanged, minus mu p plus mu integral t TP dV prime. So this does not scale. And now let's cover everything into the same units, so maybe into seconds or so. Yeah, I think I've chosen seconds. So then sigma is 3,600 to 36,000 seconds. Okay, so that is about 10 to the 4 seconds. And then I need this S divided by L. So S over L is 10 millimeters per second divided by 10 to the minus 3 meters. So I use the millimeter scale for L. And then you can work this out. So then this is actually this is equal to 10 to the minus 2 seconds. So then here I have 1 over sigma, which is then 10 to the minus 4. And this factor is 10 to the minus 2. And so I can introduce an epsilon as 10 to the minus 2. Then this is 1 over epsilon. No, this is epsilon square. And this is epsilon. So epsilon 10 to the minus 2. Then I get an epsilon here and an epsilon square here. So just as a motivation where this kind of scaling can come from. Okay. So maybe, yeah. So then sigma, no, hold on. 1 over sigma is something like epsilon square, and this S over L is something like epsilon. Okay. So then we get the rescaled transport equation epsilon pt. Yeah, and then as always, as people do this always in papers, we throw away the tilde to make it easier. And then if a student reads this the first time, they get super confused. So so now I throw away the tilde to make it easier. And so I call it then T again. Plus epsilon V times gradient P is LP. Okay. So based on these observations for E. coli, I can motivate such a scaling. And now this is called the parabolic scaling. Where tomorrow afternoon, I think we will also see some other scalings. But for now, we just look at the parabolic scaling. So now we want to do the formal limit. So formal diffusion limit. And in doing this, you will see we use all this spectral theorem, which I have here on the left-hand side. So what we do, we expand P in powers of epsilon. So we write this as P0 of TXV plus epsilon P1, TXV plus epsilon square P2, TXV plus higher order terms. And now we take this P and we sub it into the equation, and then we collect orders of equal, we collect terms of equal order of epsilon. So collect equal orders. So let's do the first one, and then you see immediately what I mean. So the lowest order is no epsilon. So I'm collecting all the terms which have no epsilon when I plug in this expansion into this equation. Right, so if I, for example, take this expansion in the first term here, I get epsilon squared times P0t, and then epsilon to the 3, epsilon to the 4, and so on. So there's no contribution for epsilon to the 0. Same here, I get a factor epsilon, but here I get something. So the equation is 0 is L P0. Yeah, the P0 carries no epsilon, so that is the leading order term. All other terms carry epsilon, so I let them out. So the epsilon 0 term, the leading order term is this. 0 is L P0. Okay. So, but we can solve this. So now we need to find a function so that L applied to this function is equal to 0. So which function does this? 1, exactly. So meaning in this context it's a function constant in V. Okay. So then from our properties here we find that P0 of Txv is actually a function which depends on x and t. Yeah, I don't know why I flip x and t, it doesn't matter. So it's a function which no longer depends on v. It is p bar of xt times 1, and then the 1 I don't write down. So it's only a function of x and t. That's the only thing. Okay. So epsilon 1. Now let's collect all the terms which have 1 power of epsilon. So nothing from here. But then from here we get v times gradient p0 equals, and from this guy we get actually the p1 term, so lp1. Okay, so now we know what p0 is. P0 does not depend on velocity, but it depends on space. So the gradient applied to p0 makes a lot of sense. There's a space dependence. And we want to solve this for p1. So can we solve this for P1? Good question, eh? So we can solve it for P1 if we have an inverse for L. Okay? So if we have an inverse, we can move it over. So do we have an inverse for L? Well, we have an inverse here. But only restricted to the subspace. Meaning, if the left-hand side of this guy is in the orthogonal complement, then we can apply the inverse. So we have a solvability condition where we need to check if this is in the orthogonal complement. Okay, so let's do that. Solvability condition is that v times gradient p0 is in this subspace 1 orthogonal. And if it is, then we can apply the pseudo-inverse f. So let's check this. So what do we need to check? We need to check integral v times gradient p0 times 1 dv. And we would like to have this to be equal to 0. So then we sub in what p0 is. So then this is integral v times p bar gradient p bar of x and t dv. And here's a dot. And now I rearrange terms in an appropriate way. So the integral acts on velocity and the derivative acts on space. So I can kind of flip the order of these terms. I can write this to be divergence of v dv p bar of xt, and maybe a bracket so that the derivative really acts on this guy, but the derivative does not act on this integral here. Okay. So is this 0? It better be, otherwise I go home and we can have go get a coffee. So why is it 0? Yeah, try it. If you have an idea, just shout it out. It's not an easy question, I think. So if again, as you see this for the first time, so the idea is this term. This term is 0 because the set v is symmetric. So for each velocity, I have the opposite velocity. So for each direction this way, I have the direction that way. And if I integrate them together, they are 0. Right? So for example, if v is Sn minus 1, then I have the circle. And so this velocity v has also minus velocity v. If I integrate them together, they are 0. So just by symmetry. Okay, so this guy is 0, and then the whole thing is 0. So cool. So we are in the orthogonal complement, so which means we can apply f. So and we do that. We can apply f, and so then we get p1 is equal to f applied to v times gradient of p0. So yeah, it doesn't look like this is going to help us much because we need this strange inverse, but I will show you in a second that we actually can compute f, and then we can really solve this. But for now, we have this formula here. Okay, epsilon square. Next terms, so epsilon square, so now this guy plays a role. We get p0t, here we get p1, and here we get p2. So p0t plus v times gradient p1 equals L p2. And now we have two ways to proceed. One would be the same thing, so we want to solve for p2. And so we need a solvability condition on the left-hand side. Actually, I write this down. Two ways to proceed. So A is solvability condition. Same as before, so we need to integrate this left-hand side by multiplying it with the 1 function. So meaning we just integrate this and say it's equal to 0. The second way is integration, where we integrate the whole equation and set it equal to 0. Now, it's the same. So these conditions A and B in this case are in fact the same. However, maybe on Friday, if I get to this, in the other case, they are no longer the same. Okay? So in this case, here they are exactly the same. But later, we use B. So just to show you already here what kind of the crucial step will be if we do it later for the other case, for the anisotropic case, it will be right there where we use integration instead of the solvability condition. So just a little detail. But so let's do that. Now let's do that. So so let's say the solvability condition would be integral v p0t plus v times gradient p1 dv is supposed to be equal to 0. So I put an exclamation mark on top. So we want it to be 0. That is the condition. So solvability. So let's sub in what P0 is and then sub in P1. So then we get this is integral V, this is P bar T plus V times gradient P1, and P1 is F of V times gradient P bar, and then dV. And now let's try to simplify this integral here. So first of all, this guy, P bar does not depend on velocity. So this is really just the size of V times P bar T. Right, so I integrate over dV, but the thing does not depend on V. But this guy certainly depends on V. This depends on V a lot. And then we have this strange multiplication with the divergence or with the gradient. But we can write it in a very smart way, like this. So I write this as divergence times integral V F V dV times divergence P bar. So I'm not sure if this is too fast or not. So what I've done here, I mean, here I have the product of a vector times a vector, so I write it the other way. And then I can take the gradient out of the integration because this works on velocity, this works on space, not on velocity. But I keep the vector product from here to here. Then there is the f. The f does not depend on space, so the derivative does not act on this, although the order is still correct. And then here I do the same thing. I take this, which is gradient now, I take it out of the integration and put it here. Okay. So if you, we can also write it component-wise. Why not? Sure. So if I write this here component-wise, I get first term. The first term is clear, but then this is vi delta I integral f vj delta j p bar dv, and then this one here is v times p bar t. And so now I move this di to the front and this dj to the back, so then I have di integral vi f. Oh, the integral sign is wrong here. Must be here. Vj dv times dj p bar. And then I use summation convention over repeated indices, right? It's the sum over I and j. Aha, but this looks actually better, because now we can see that this guy here is actually a matrix, right? It has entries ij. This is a tensor or a matrix. So it's called the diffusion tensor. Yeah, this will be, is this a diffusion tensor or is there another factor? Let me just see. It's almost the diffusion tensor. So let me write this down extra over here. So I take this equation and I divide by this v absolute value. So then I get pt equals divergence of d gradient p bar. Okay, where then d is a diffusion tensor, which is 1 over v integral v vf v dv. And now we understand this this term to be a matrix. So here we use kind of the dyadic product of these v terms. This is a matrix. We put it here, and this is our diffusion equation. Okay. So diffusion limit. Okay. Yeah, and then as you saw it component-wise, so I think you can make sense of these terms now. But this is cool. So we started with the scale transport equation here, and then we find the leading order term p bar, and then we find this has to satisfy the diffusion equation, but then this d is actually a matrix, which is given by this funny pseudo-inverse, which shows up here. So let's come back to the Pearson walk and compute this f. Example Pearson walk. Because I want to show now that this is actually not scary. So I think we did the worst of it, of all the function analysis. From now on it should get easier, I hope. So Pearson walk, so we had v is equal to sn minus 1, and we had t vv prime is equal to 1 over v. So let's compute f. So given phi in one orthogonal, we need to find a z in one orthogonal such that L of z is equal to phi. And if we can do this, then z is the inverse of phi. Yes?
Do they have the same sign, the equation over there and the diffusion equation?
Do I need a minus sign? I need a minus sign. Thank you. You're right. So here, good that you spot this, because it's very important. We will find f is negative, and so then this will eat up the sign here. Thank you. Yeah. So given phi, we want to find z, so that z solves this equation, and then z is the inverse of phi. So let's write down this equation. So Lz is minus mu z plus mu integral t of v prime z. What am I doing? Oh yeah. And I'm in a Pearson walk, so I can write this as 1 over v z of v prime dv prime. And this has to be equal to phi of v. But z is in the orthogonal complement of the constant functions, meaning this integral is 0. Right? This is just a constant here, so we just integrate z with the constant, so this is 0. So this guy is 0, since z is in one orthogonal. So, but then what do we keep? We keep minus mu z equals phi. So now we can solve it for z. So then this implies z of v is minus 1 over mu times phi of v. Okay? And then we have the inverse. So the inverse is just this minus 1 over mu. That's all there is. So this implies f is actually minus 1 over mu as multiplication operator. So it couldn't be simpler, I think. It's really surprising. You first start with this function analysis and this pseudo inverse and blah blah blah. So in an application like this, you get actually something really manageable. Just multiplication with minus 1 over mu. So we have this f. Now we put this f here to get our diffusion coefficient. So where am I? This guy. So then d is 1 over mu v integral v transpose dv. So now I add this transpose vector on v to really indicate it's a dyadic product, so that I get a matrix coming out of this. And the minus sign was important, right? As I said, the minus sign eats the minus sign from here, so that all fits together. So now it's a positive term. Okay. So now we need to compute this integral v transpose dv for the set v, and the set v is given here. It is, where's my Pearson walk? So it is s times Sn minus 1. So I have vectors of length s, and I need to integrate their dyadic product. So how to do that? This doesn't seem to be so straightforward either. Let's see. So v is s times Sn minus 1. So if I go in 2 dimensions, for example, then I can write v as s times cosine theta sine theta. Right, so I just have unit vectors with a certain angle. And theta is okay. And then this dyadic product, v transposed, this is an s square cosine square of theta cos times sine, and sine times cos, and sine square. So you would have to take this matrix and then sub it into the integral and integrate these trigonometric functions. So this is certainly manageable. Maybe you have done it in some of your classes before. But this only works in 2D so well. So if you have 3 dimensions, then this matrix has this cosine theta, sine phi, and cosine theta, cosine phi, and so on. So you have to integrate already 2 angles. And in higher dimensions, I mean, at some point you get your limit in trigonometric integration. It's also very cumbersome. So I'd like to show you a new method, basically a PDE method to solve this integration. But then we can solve it in any dimension. So this method is really cool, and we can do it for any dimension, really. So better, or let's maybe write complicated in higher dimensions. So better, we use the divergence theorem. Divergence theorem. Okay. And so maybe I formulate this as a lemma. So lemma 8. Now, I'm kind of, I'm sure that my numeration doesn't make any sense. But at least I know that 8 is bigger than maybe 5, which was the last number. So it is still monotonic, even if there are things missing. So this is something which I did a few years ago. So we have V is Sn minus 1, and omega 0 is Sn minus 1. So then the size of V is S to the n minus 1 omega 0. Okay, so I just introduced omega 0 for the size of the unit sphere. Okay, and then if we have a speed s, then the unit sphere scales with Sn minus 1. So that is this, but we need that the integral v transpose dv is given by omega 0 s to the n plus 1 divided by n, which is a space dimension, times the identity. So we need to get a matrix out of this, and what we get is the identity matrix with a certain scaling factor in front. So really cool thing. I mean, if you do the 2-dimensional integration, you might be able to see this. Well, you see this quickly. Here in this case, sine and cosine are orthogonal, so this integrates to 0, and this as well, and this integrates to a value. So here we have the identity matrix, but we can do this in any dimension. Yeah, I like to show the proof because this method is kind of new in this context. Yeah. So I take 2 test vectors, A and B and Rn, and then I apply them to my matrix which I'm looking at. So then I look at A applied to V transpose dV applied to B. Yeah, so as with the 2 test vectors A and B. All right. Good, and so then I write this down component-wise. Then this is integral V, AI, VI, VJ, BJ, dV. And I move the a's into the integration because they're just constants, so there's nothing to be done. And then the first vi I normalize to become a unit vector. I write this as S integral V vi divided by size of V, which is S, times AI VJ BJ dV. So I'm just writing the first velocity vector a little bit different. I normalize it here, and then I make up with the speed s in front. Okay. But now I'm integrating over the what is it called? Over the sphere. Yeah, I'm integrating over the sphere, and then this vi over v turns out is actually the normal vector here. It's the orthonormal vector. So I'm integrating over a surface with a normal vector, which is the same as the divergence of the whole thing over the whole ball. Right? So then, using divergence theorem, this is integral over the ball of radius s around 0, divergence with respect to vi of ai, vj, bj, dv. So that is the main trick. You understand this as a divergence theorem. And then you can apply. This is now the v derivative of this term. And v appears here in a linear fashion. So I can easily differentiate with respect to vi. And then I get in delta ij. Right? I only get a derivative is if j equals to I. So then this is s times integral bs0 ai bi dv. Okay, and then this can be written as to be s times bs0 times ai bi, and so here you see that the identity matrix shows up. It's really only the entries ai bi, so it's the identity matrix, and this is the factor in front. So then what is missing is to compute the factor in front. And let's maybe do that quickly as well. And then I finish for today. So we need the size of the unit, the ball of radius s around 0. So this is s to the n ball of radius 1, which we can write as s to the n integral ball of radius 1 dv. And then we use the divergence theorem again. So this is s to the n divided by n, integral ball of radius 1, divergence v of v dv. So if I take the divergence of the vector v, I get n, right? dv1 by dv1 and dv2 by dv2, etc. I get n, and here's the n from here. And then I use the divergence theorem again, forwards. So s to the n over n, integral over Sn minus 1 of, what do I get, n times v? Yeah. So sigma times sigma d sigma. Right. So now v has unit length, and the normal vector has unit length, and the normal vector is the same vector as v was. So I get this. Now this product is equal to 1. So then I get s to the n divided by n times omega 0. Omega 0 was the size here of Sn minus 1. Good. And so now I put this all together. So I take this here. I get one factor in addition of s, so I get s to the n plus 1, and everything else as written here. So, and it's this. Okay, so a few remarks about this, but really I'm almost done for today. So that is this. So remarks for general symmetric v, there exists a kappa, so that integral v transpose dv is kappa times the identity. So I discussed other symmetric sets v, and so we can have a similar result for that case. That's the first remark. And second, yeah, so in this paper which I mentioned, 2002, we also compute all higher moments, higher velocity moments. So integral v, vi, vj, blah, 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 vn, dv can also be computed. With the same method as here. Good. So that is now let's put it together with a Pearson walk. So what do we do? Now this guy is here. We put it here. We get this factor 1 over mu v for the diffusion coefficient, and then we put it into the diffusion equation. So let me write this down. For the Pearson walk, finally, the Pearson walk has a diffusion limit of p bar t equals s square divided by mu n times Laplace p bar. So if you plug everything in backwards where we came from, then this is what we get. So it is isotropic diffusion. It's actually a standard diffusion equation, and the diffusion coefficient is given by s squared divided by mu n. Yeah, so that is this. Good, so that's a good place to stop. A few minutes before the next lecture starts. Thank you very much.